The world around us is made up of countless particles, ranging from the atoms that make up the air we breathe to the cells that make up our bodies. But what are these particles made of, and how do they interact with each other? If we look at the body on a macroscopic level, we see a collection of cells that work together to form tissues, organs, and ultimately, the entire organism. But if we zoom in closer, we see that each cell is made up of countless particles, including protons, neutrons, and electrons. And if we zoom in even closer, we see that those protons and neutrons are made up of quarks. In fact, the entire universe can be thought of as a vast collection of quarks and other subatomic particles, all interacting with each other through the fundamental forces of nature. This perfection is all the more remarkable when we consider the universe's history, from its birth in the fiery explosion of the Big Bang to its ongoing expansion and evolution. Despite all the chaos and destruction that has occurred in the universe, the fundamental laws of nature have remained constant, providing a stable foundation for the emergence and evolution of life. It's difficult to look up at the night sky and not be struck by the sheer perfection of the universe. Everything seems to have been designed with meticulous attention to detail, from the countless galaxies and stars stretching across the heavens to the intricate, interwoven systems that govern the universe's behavior. And nowhere is this perfection more apparent than in the delicate balance of physical constants that allow for the emergence of life. The universe is eerily, uncannily perfect as a setting for creating life. All of the physical constants that govern the universe's behavior, from the speed of light to the ratios of the four fundamental forces, seem finely tuned to allow for the emergence of life as we know it. If any of these constants were even slightly different, the universe would be inhospitable, incapable of supporting the complex chemical reactions and biological processes that make life. This level of precision and fine-tuning has led many to wonder, why is the universe so perfect? How did all of these physical constants become so perfectly calibrated to allow for the emergence of life? Is there a purpose behind the universe's perfection, or is it simply a coincidence? At one time, people around the world believed that the universe consisted of a flat Earth surrounded by the sun, the moon, and the stars. Over time, ancient astronomers became aware that some stars did not move like the rest, and began to understand that some of these objects were planets. In time, astronomers then also began to understand that the Earth was indeed round, and came up with rationalized explanations for the behavior of other celestial bodies. And by classical antiquity, scientists had formulated ideas on how the motion of the planets occurred, and how all the heavenly orbs fit together. For about 1,400 years, humanity believed that the Earth was at the center of it all, with the sun, moon, planets, and stars revolving around the Earth. Which is what we refer to as the geocentric model of the universe. An astronomer named Eudoxus created the first model of a geocentric universe around 380 BC. This geocentric model of the universe was the prevailing view for much of human history, but it was not without its problems. Ancient astronomers noticed that some of the planets seemed to move backward in the sky at certain times, a phenomenon known as retrograde motion. To explain this, they came up with increasingly complex models involving crystal spheres and tiny circles. This theory was further refined by Ptolemy. Ptolemy argued that the Earth was a sphere in the center of the universe, from the simple observation that half the stars were above the horizon and half were below the horizon at any time, and the assumption that the stars were all at some modest distance from the center of the universe. If the Earth was substantially displaced from the center, this division into visible and invisible stars would not be equal. But in the 16th century, a Polish mathematician and astronomer named Nicolaus Copernicus presented a radically different universe model. His heliocentric model placed the Sun at the center of the solar system, with the Earth and other planets orbiting around it. It took some time for Copernicus's ideas to gain widespread acceptance, as they challenged long-held beliefs and went against the established authority of the Catholic Church. But over time, observations by Galileo and others helped to confirm the heliocentric model, and it gradually became the prevailing view in the scientific community. The 20th century brought about massive advancements in technology and our ability to study the universe. As astronomers peered into the heavens with ever larger telescopes, it became clear that the Sun is just one of the billions of stars within our Milky Way galaxy. And the Milky Way, in turn, is just one of potentially trillions of galaxies in the observable universe. But the realization that we are just a small part of a vast and expansive universe didn't stop there. With the work of scientists like Edwin Hubble, we learned that the universe is not only vast but also expanding. This led to the development of the Big Bang theory, which states that the universe began with a massive explosion 13.8 billion years ago. All of these discoveries have led us to ask the question, are we special in the universe? The answer, it seems, is both yes and no. On one hand, we are just one species on one planet in a vast and ever-expanding universe. But on the other hand, the conditions that allowed for our existence are incredibly specific and rare. From the tilt of the Earth's axis to the precise placement of the Moon, our planet and its surrounding environment are perfectly suited for life as we know it. Sometimes, you can only resort to the most basic of assumptions, that however the universe may behave, it behaved in a way that allowed it to give rise to intelligent observers like us. This line of thinking is known as the anthropic principle. Nobody doubts that the universe exists, that it obeys fundamental laws, and that we, like everything else in this universe, also obey those same rules. We arose naturally, and therefore the universe must have properties that at least make it possible, if not mandatory, for intelligent, living observers like us to arise. The anthropic principle came about in 1973 when physicist Brandon Carter made the following two statements. We must be prepared to take into account the fact that our location in the universe is necessarily privileged, to the extent of being compatible with our existence as observers. The universe, and hence the fundamental parameters on which it depends, must be as to admit the creation of observers within it at some stage. The first statement is now known as the weak anthropic principle, which simply states that the universe must be such that we could have come into existence within it. The second is called the strong anthropic principle, which states that if no one arose in the universe, we'd never be here investigating it. However, these interpretations of the anthropic principle fail to recognize that probability is not an objective absolute, but rather, it's relative to a set of specific conditions. Once all the conditions are established, the probability of an event occurring becomes either 1 or 0. Therefore, the existence of life does not imply that the universe is perfect. Moreover, relying solely on the anthropic principle to explain the perfection of the universe ignores the fundamental goal of science, that is, to understand the natural processes that shaped our universe. The scientific inquiry aims to uncover the mechanisms that led to the current state of the universe, not to use anthropic arguments to explain its properties. The anthropic principle is a useful starting point for exploring the constraints on the properties of our universe. Still, it is not a complete scientific explanation in and of itself. But where does that leave us? In the medieval era, philosophers and scholars grappled with the nature of the universe and the origins of life. One such thinker was Sigurd of Brabant, a 13th century philosopher who authored the thesis, The Eternity of the World. Sigurd was born in Brabant, a region in modern-day Belgium, around the year 1240, and studied in Paris, which was then the center of the intellectual world. In Paris, Sigurd was associated with the radical Aristotelian movement, which sought to reconcile the teachings of the ancient Greek philosopher with the doctrines of Christianity. This movement was led by figures such as Averroes and Avicenna, who had translated and interpreted Aristotle's works, and who argued that philosophy could be used to supplement and deepen religious faith. Sigurd was deeply influenced by these thinkers, and his own philosophy emphasized the importance of reason and the power of human intellect. He argued that philosophy was a necessary complement to theology and that the truths of faith could be illuminated and made more understandable through the use of logic and argumentation. In his thesis on the eternity of the world, Sigurd challenged the traditional view that the universe had a definite beginning and that it had been created. Instead, Sigurd argued that the universe had always existed and that it was eternal and self-sufficient. According to Sigurd, there was no first man, and no first specimen of any particular species, and the physical universe was without any first beginning. Sigurd's thesis was highly controversial, and it sparked intense debate among scholars and theologians of his time. Many argued that Sigurd's ideas were heretical and threatened the foundations of the Christian faith, while others saw in them an opportunity to deepen and enrich their understanding of the world. However, Sigurd's idea of an eternal universe found new life in the 20th century with the steady-state model. According to the steady-state model, the universe is perfect because it has always existed in a state of balance and symmetry, with new matter being constantly created, to replace the matter that is lost as the universe expands. This theory was developed in 1948 by Fred Hoyle, Hermann Bondi, and Thomas Gold. It was founded on what's now known as the perfect cosmological principle, which hypothesized that the universe wasn't just the same, on average, everywhere in space, but also in time. That no matter when you looked at the universe, on average, you'd always see the same thing. This is the core tenet of the steady-state theory, that the universe isn't just the same everywhere, but also everywhen. The steady-state universe isn't just eternal, but timeless. According to this theory, the universe has always been in a state of perfect balance, with just the right amount of matter and energy to maintain its expansion. This is one of the theories that can at least explain why the universe is so perfect. But however, just like other theories, there's a catch. Even though the theory was so good that even Einstein favored it, problems with the steady-state model began to emerge in the 1950s and 60s, when astronomers discovered the accelerated expansion of the universe, radio galaxies, and quasars that are only observed at high redshifts. However, the real nail in the coffin of the steady-state theory was the discovery of cosmic microwave background radiation in 1965. This is a weak background radiation that fills the whole of space and is the same in all directions. This paved way for the Big Bang theory, which is considered the best explanation of the origin of the universe, which states that the universe expanded from a very hot, very dense, and infinitesimally small point, called a singularity. In the Big Bang theory, this radiation is a relic or snapshot from the time the universe was young and hot and was predicted before it was even discovered. However, in the steady-state theory, it is almost impossible to explain the origin of this radiation. The idea that the universe expanded from a single point was first presented in a scientific paper by a Belgian cosmologist and Catholic priest, Georges Lemaitre, in 1931. He proposed the existence of a prime-val atom, where the fabric of space and time originated. In 1927, years before he presented this idea, he also submitted a paper discussing his derivations on Einstein's equations. It led him to conclude that the universe is expanding and that the speed of the galaxies is proportional to their distances. In 1929, Edwin Hubble presented more updated and detailed data, establishing the proportionality between the distances and the speeds of the galaxies. In 1964, George Gamow proposed the idea that the universe expanded and cooled from an initial state of infinite density and temperature. He added that all protons, neutrons, and electrons have been present in that ocean of high-energy radiation. His calculations also explained the relative abundances of hydrogen and helium, but not the heavier elements. This leaves us with one vital question. Have the laws of nature remained the same since the Big Bang some 13.8 billion years ago? In the 4th century, Aristotle argued that one of the major goals of physics was the study of change. If the laws of physics that we knew have changed with time, then we can ask for the reason behind this change, and call that a law of physics instead. If that in turn appeared to change, then again, we can ask for the reason behind this change. One does not expect this to go on, eventually, it will come to a stop. And we have a physical theory that is independent of time. If any of the fundamental forces of the universe were to change, the results would be catastrophic. Here in our modern universe, we've got gravitation, electromagnetism, and the strong and weak nuclear forces. If any of these forces weren't constant, it's easy to imagine how haywire the universe would get. If the force of gravity weren't constant, the consequences would be far-reaching and potentially disastrous. Reliable predictions of object motion on Earth, celestial orbits within our solar system, flight paths of aircraft and spacecraft, and cosmic phenomena such as gravitational lensing and universe expansion would be virtually impossible to make. Same thing goes for electromagnetic force. If it weren't constant, electrons in orbit around atomic nuclei would see their orbitals and energy levels change, and the binding properties between electrons in different atoms would become highly uncertain. In other words, every molecule in the universe, if the electromagnetic force changed, would alter its properties in a fundamental fashion. If this happened where entities like human beings exist, would be immediately thrust into an unsustainable configuration. If it occurred on Earth, life would immediately come to an end. And if the strong or weak nuclear forces changed, it would bring about a level of catastrophe that would be swift and severe, leaving little time for us to even comprehend what was happening. Stable atomic nuclei would undergo spontaneous decay, releasing a tremendous amount of energy as they shifted into a more stable configuration. Bound atoms would be stripped of their electrons and transformed into ionized particles, resulting in the creation of a plasma universe in the affected region. The consequences of such a disruption to the fundamental nuclear forces would be so profound that it's impossible to fully comprehend the scale of the devastation that would result. Our universe must have been born with lumps, but if we're different than this, the masses of those lumps would have been very different. If it was much smaller, there'd be no structure at all. Much larger, and we could have had a universe catastrophically filled with black holes from a very, very early time. To give us the universe we have required an extremely fortuitous combination of circumstances, and lucky for us, the one we were given looks to be just right. We happen to live in a universe that supports life because, if we didn't, we wouldn't be here to wonder about it. But what if the fine-tuning of our universe is not remarkable because there are countless other universes that have different physical constants and laws of nature? In Dublin in 1952, Erwin Schrödinger gave a lecture in which he jocularly warned his audience that what he was about to say might seem lunatic. He said that when his equations seemed to describe several different histories, these were not alternatives, but all really happened simultaneously. This sort of duality is called superposition. According to David Deutsch, this is the earliest known reference to many worlds. This implies that all possible outcomes of quantum measurements are physically realized in some world or universe. Imagine that the universe we observe, from end to end, is just a drop in the cosmic ocean. Beyond what we can see, there's more space, more stars, more galaxies, and more everything, perhaps billions of light years farther than we'll ever be able to access. And that as large as the unobservable universe is, there are again innumerably more universes just like it. Some might be larger and older, some smaller and younger, dotted throughout an even larger space-time. As rapidly and inevitably as these universes expand, the space-time containing them expands even more quickly, driving them apart from one another, and ensuring that no two universes will ever collide. This is the scientific idea of a multiverse. But if the science we accept today is correct, it's not only a valid idea, it's an unavoidable consequence of our fundamental laws. The idea of the multiverse has its roots in the physics required to describe the universe that we see and inhabit today. As we peer out into the cosmos, we are confronted with a seemingly infinite expanse of stars, galaxies, and cosmic structures that stretch across vast distances of space and time. The more we look, the more we see, and the more questions arise. If we go all the way to the limits of what we can see, we find the very earliest stars in the universe, and then a region of darkness beyond that, where the only light is the leftover glow from the Big Bang. But the Big Bang itself, occurring everywhere some 13.8 billion years ago, wasn't the start of space and time, but rather the start of our observable universe. Before that, there was an epoch known as cosmic inflation, where space itself expanded exponentially, full of energy inherent to the fabric of space-time. In 2007, Nobel laureate Steven Weinberg suggested that if the multiverse existed, the hope of finding a rational explanation for the precise values of quark masses and other constants of the standard model that we observe in our Big Bang is doomed. For their values would be an accident of the particular part of the multiverse in which we live. This picture of huge universes, far bigger than the meager part that's observable to us, constantly being created across this exponentially inflating space, is what the multiverse is all about. That there are other universes that might not favor intelligent life like us. That our universe is just perfect for us. It's important to recognize that the multiverse is not a scientific theory on its own. It makes no predictions for any observable phenomena that we can access from within our own pocket of existence. Rather, the multiverse is a theoretical prediction that comes out of the laws of physics as they are best understood today. It's perhaps even an inevitable consequence of those laws. If you have an inflationary universe governed by quantum physics, this is something you're pretty much destined to wind up with. In 1913, Lawrence Joseph Henderson made a significant contribution to the study of the universe's fine-tuning with his book, The Fitness of the Environment. Among the first works of its kind, the book delved into the critical role of water and environmental conditions in sustaining life. Henderson noted that life's existence depends entirely on the Earth-specific conditions, particularly the abundance and properties of water. Building on this foundation, physicist Robert Dicke postulated in 1961 that the universe's physical forces, including electromagnetism and gravity, must be finely tuned to allow for life to thrive. Similarly, in his 1984 book The Intelligent Universe, Fred Hoyle argued that numerous non-biological phenomena appeared to be essential to the existence of carbon-based life forms such as humans. As Hoyle put it, the list of anthropic properties, apparent accidents of a non-biological nature without which carbon-based and hence, human life could not exist, is large and impressive. Such convictions about the universe's fine-tuning led many to believe that the Large Hadron Collider would uncover evidence of physics beyond the standard model, such as supersymmetry. However, despite expectations, by 2012, the collider had not yielded proof of supersymmetry at the energy levels it was capable of probing. Despite these competing theories, there's no denying the fact that our universe is indeed remarkably consistent and well-ordered. The speed of light is the same in every corner of the cosmos, the laws of thermodynamics hold true from the smallest particles to the largest structures, and the ratio of the strong force to the electromagnetic force is just right to allow for the formation of stars and galaxies. Alter the relative strengths of gravity and electromagnetism a little bit, stars and galaxies can't form. Flip the tiny difference in the proton and neutron's masses to make the proton heavier, and you don't even get stable atoms. Changing these numbers would probably preclude any life in the universe. It isn't a big leap to say it looks like the knobs have been twiddled, as if the universe were somehow fine-tuned for our existence. But what does all of this mean for us? Well, it suggests that there's something special about the universe and the way that it operates. It points to a sense of purpose or meaning that extends beyond our individual lives and experiences. It reminds us that we are part of something much larger and more intricate than we could ever fully comprehend. So the next time you look up at the night sky, take a moment to marvel at the perfection and consistency of the universe. Let it remind you of the incredible mystery and beauty of the world we live in, and of our place in the grand scheme of things. But one of the biggest challenges now is, how can we find a theory that can link up everything in the universe? Like a magic theory? I have already made a video on that. Click the video up on your screen to watch it, and I'll see you there. Thanks for watching and subscribe for more videos.